This video will show how to use the investigative mode in Adapt Builder 2018. In the video we're going to import a slab and we're going to add reinforcement to the slab. We're going to also include post-tensioning, and then we're going to evaluate the slab for moment demand and capacity as well as the stresses on the slab. We'll go ahead and in the Builder 2018 splash screen we're going to expand this down, and we're going to be using Floor Pro. We're going to have the PTRC mode so we can model the post-tensioning and also the US unit system. We'll select OK. And to begin the project we're going to use an IMP file that was generated from Revit using the Adapt Revit link, and we're going to import that file for the model into this version of Adapt, so of Adapt Builder. So we'll go ahead and use the File menu. We're going to select Import IMP, and we'll go ahead and navigate over to the location where we have our file. We'll use this m1.imp file. And when we do this, the program will open the Import Options dialog. So this Options dialog will list components that are included within the IMP file. And you can see here under Create New Model, it's basically selected to all, and that means everything will come in. If we select Update Level, then we can import any level that is included in the IMP file. For example, level 4, this would filter the components on level 4, and then these are editable at that point. You can deselect components that you do not want to import. So in this case we are going to import, we're going to go down and import actually level 3. So we'll import level 3. For the reference plane, by default when you build a new model in Builder, there are 3 planes. There's the current plane, I'll call that C. There's the top plane, I'll call that T. And then the bottom plane, which is the base, we'll call that B. So we want to import this particular level, level 3, into the current plane. That's the first elevated plane. We're going to have columns and walls potentially below this plane and also above this plane. But this is the plane that will include reinforcement and some post-tensioning for this existing slab. Go ahead and clear that. And we'll go ahead now to loads and load cases. In loads and load cases, there's nothing that was imported or generated in the IMP file. In other words, the Revit model did not include any loads as well as combinations. We'll just load the model inside of Builder. So once we're done there, we'll select OK. And if we select OK, we're going to go down to the, or excuse me, up to the top right, and I'm actually going to use multi-level mode. And I'll just select this, and then I'm going to use Zoom Extents. So I'll go to Home, here under Zoom Extents. That's also shown at the bottom Quick Access toolbar there. So I'll select that, and you can see that this is actually showing every level in the sequence of levels. In this case we only have current plane. So we're going to be working in single level mode. This is a single level model. So I just switched over here just to see that there was some model there. If I go back to single level mode, we're now at the active plane, which is the current plane. We're working on that plane right there. And this is the model we're going to be, or the slab we'll be using to build some user-defined reinforcement as well as post-tensioning. Okay, this slab, if we double-click, we can open the properties. This is an 8-inch slab. The default material is concrete 1. So the first thing we want to do is make sure we have the materials set up. We're going to go up to Criteria under Concrete, and I'm actually going to add a couple of new concretes. We're going to call this 5,000 psi, and we'll call the next one 6,000 psi. And then we want to make sure we update the properties, numerical compressive strength here, as well as the modulus of elasticity. The self-weight, here this entry is actually used to calculate the modulus, so make sure you have the proper inputs here, and then we'll do the same for the 6,000 psi concrete. We'll select OK, and we're now going to go ahead and make sure that these materials are assigned. So if I select the slab again, we're going to select 5,000 and I'll press the green checkbox to accept that. I want to also select the walls and columns and change those, but there are multiple walls and columns. Here there's only one slab, so I can go ahead and open that one input. But if I select all of my walls and columns, I want to deselect the slab. So I have a couple ways. I can Windows select and then press Control and select the slab to deselect it, or I can go to a side view, and again from Home, Zoom Camera. I'll go to a side view and just select my upper and my lower supports. Okay, and if I go back to my, let's say, 3D view of the structure, let's go here, we can see that those are selected. So now I want to modify a group of components. I want to modify a selection, so we'll go to Modify, Selection, and we'll go to Material, and we'll set this as 6,000. Okay, so that's done. We're now going to load the slab. So we're going to put some base load on the slab. This might be the design loads that it was designed for originally. By default, if we go over to loading, load cases, there are, I'm going to turn off lateral load sets. This doesn't apply. There are dead loads and live loads. These are superimposed. Live load is unreduced by default. So the self weight is auto calculated by the program. So we're going to use these two reserved load cases, and then we're going to create an additional one that will be called future. I'll just call it future tenant for the additional load that we're going to place on the slab, and we'll select OK. As the user, you can enter as many load cases as you need and name them whatever you'd like. Just avoid using special characters in the load case names like slash, pound sign, percentage, dollar sign, etc. I would just use underscore as a separator. That's a recommended practice for most naming conventions within the program. So we're going to select the slab, and I'm actually going to map loading to the slab. So we'll go to loading under patch load wizard, and for the dead load I'll say that this is 0.02. This is in KSF, and then I'll go back to patch load wizard, select live load, and this is 0.05, we'll say. So that works well if you want to map loading to a selected slab region or a selected polygon. Note also that the loading is cumulative. If I add a load on top of this load, it's cumulative. You could also add negative loads in the upward direction as well. So let's go now to the top view. We have our base loading. We're going to again assume that this is a loading that the slab was designed for. It's the total service load, for example, from the original design. And now we're going to add this new tenant load. So we're going to assume that in this region here there is an additional new live load of 100 PSF. Actually, we'll use something a little smaller. That might be excessive. So we'll say 75 PSF. So 75 PSF. And in this case, I can't map the load to this slab region because I don't have a slab there. So I have to use the general option to just add a patch load. I'll select Add Patch Load, and I now have two options. I can either enter the load first, meaning the load polygon, or I can directly go to the load properties to define the load case and the magnitude. Otherwise, I have to do it after the fact. So I'll just go to Modify, Properties. That will open the properties for the patch load, and we'll say Future Tenant, and this is 0.075. And now I can just click anywhere outside of this box and begin drawing that load. Now you'll see I'm hovering over corners. I want to basically snap to a corner of the slab, but I can't. I need to go down to the bottom, and these snap tools are all docked at the bottom. So I'll select Snap Tool, and I'm just going to trace the outline of this slab. Okay, we'll go there, over here, and then over on this side we're going to go all the way perpendicular to the slab edge, so we'll say right there, and then work our way back up to this upper corner right there. And you'll notice I actually forgot to put one point in there, so that's okay. I can right click, close, or just press enter. And after the fact, I want to exit out of this command. Notice I'm still in the command. I just drew one polygon, but I'm still in the loading command. So if I right click and press exit, or I can just press escape on the keyboard, that will get me out of the command. I'll select the polygon, right click, insert a vertex, and then add a point, escape out of there, and then just drag the point over, and that allows me to add a new point. Let's go ahead now and save the model. So I'll save as. So we're going to call this 2018 Investigate. Make sure again in the naming of the files that you use underscore as a separator, and use or avoid using special characters there also. So we now have our additional load here. Now we may not really care, it may not be part of the evaluation, rather, of what's happening over in these two bays here. We're basically wanting to evaluate this bay and also this bay here, or this frame line, and then also in the opposite direction. It's a two-way slab, so we're going to evaluate it as such. The next step will be to add reinforcement. We want to add existing reinforcement. I'm not going to add all of the reinforcement here. I'll add just the reinforcement that where I'm kind of focusing my checks for. So I'll add the reinforcement up here. I'll add the tendons here, and then I'm going to add some tendons, in this direction also. Again, those technically don't have to extend all the way down to the opposite slab edge if our only focus is really what's happening here. They can, and it's just as easy to do that as well. But if you have a really large slab, it may not be necessary to model every detail that's not associated with the immediate region that you are evaluating. Alright, so we're going to use we're going to go ahead and use the reinforcement or rebar ribbon here to add and model reinforcement. Now, there's three types of reinforcement that we can add. We can add a rebar mesh, top or bottom. We can add banded reinforcement, or we can also add distributed reinforcement. So we're going to add, we're going to start with adding banded reinforcement over these columns here and the end of this wall. And we're going to just use some arbitrary selections for the banded rebar. So I'll first start by just selecting banded, and I will go ahead and just draw in a piece of banded rebar. And I can change the, you can see once I click a point, it actually, the dynamic dimensioning will show me the length. We'll just assume it's 15 feet here. Now that might be, this might be L over 6 clear span to one side. So we'll just assume that's 15 feet, and in the other direction we're going to do the same. We're going to add this bar here, and this we're going to say is, let's say it's 8 feet. Okay, and then these are both bottom bars, so we're going to change those first to top bars. So we'll just go here to top. Notice it's tagged as base reinforcement. We can enter the number of bars. We're going to assume this is 5 bars, 8 feet, and the cover we'll say is 1 inch. And then we'll change this one also to top, 5 bars by 15 feet, cover is 1 inch. Okay, and then we're going to go ahead and just take these bars, and I'm going to select them and press Control-Shift-C to copy them. And I'm going to select, using the snap to endpoint, just the center of the column as my reference point. So I'll put these bars here, and then I'm actually going to adjust their lengths. I'll come back and do the walls. Okay, so this bar, I'm just going to take this point and just drag it. If I wanted to manipulate the length, I could also just come here and say, well, I want to make that bar 13 feet, and then I could reposition the bar by moving it. How do you move the bar? Well, I would either have to stretch the endpoints, I could copy paste it and then delete out the original bar, or I can go to the option for modify, and then we're going to move by using the in plane. And I'll just select this point. Maybe I want to move it here. Let's try that again. So we're going to select the rebar, say move in plane. It says select the start point of the vector. We're going to move from here, endpoint, to here, and we'll say move, and that will move the bar down. So there's different ways to move the bar. My recommendation is probably just to stretch it and use the dynamic dimensioning. The dynamic dimensioning has a stretch increment or a move increment. So if you select, right click, or if you go to if you start to move this point and then right click, you can go to dimension input, or you can go up to home, settings, dynamic dimensioning, and this allows you to change the length increment here. Okay, so now let's go ahead and stretch this bar. Okay, this is now 11 foot 4 inches, and if I wanted to stretch it down more, I could stretch it down a bit more. That positions or resizes the bar rather. Here I'm going to stretch this bar in this way. I'll use snap to nearest so I can snap right on top of the existing bar, and then we might want to, lengthen, increase the length of that bar to some dimension. Okay, we'll do something like that. That's 1310. Let's go ahead and say 15, and then I'll just take this bar, Control C, Control V, and move it, copy it there. Now in here I'm not using a reference point. I'm basically just eyeballing the position of the bar. Let me try that again. Control C, Control V. Okay, there we go. And last bar for the columns here will be this one. And again, I could have moved this, but I'm just basically adjusting the endpoints and doing something like so. If you don't want to copy paste, you could just enter the bars individually at every column. You don't technically have to copy paste like I did. You could come to the reinforcement or the rebar ribbon, select banded, and just enter every bar uniquely. And so we'll do that here near the walls. I'll go ahead and select banded again. I'm going to add a bar along this wall, and you can see that bar, and then I'm going to add a bar along this wall here, something like that. Do the same thing over here, and then we'll go ahead and change the length of the bars as needed, like so. I'll say this is 6 number 5 bars, and the length I'm going to say is 20 feet. And then here we're going to use 6 number 5s. And I'll say the length here is 24 feet. On the opposite side, we've made these also 20 and 24 feet. And then we've made sure that these are all set to top bars by double clicking, selecting top. So those came in as bottom. We just had to change that. Now in the bottom of the slab, we're going to assume that there's a number 5 by 18 inch on center mat of steel, in addition to some extra bars located in these outer bays in the slab. So we'll show that process. We're going to go to the model base rebar from the rebar ribbon and select mesh, and I'm just going to select the corners of the slab where I want the mesh. So we'll make sure I have only the endpoint snap option turned on. This makes it a little bit easier to snap to these points. And then I'm also going to go back now and turn on snap to nearest, because I want to just snap on the slab edge further down from the area where we're working, just to ensure that we have the proper bars inside of the design strip that we're going to generate. And then we'll go ahead and complete this polygon. I'll snap on all of these corners here, press C to close, and then escape to exit. Now this is a top mesh, so I double click on the mesh. I'll go to bottom. We're going to select bar size as compared to area, and we'll say this is number 5 is at 18. Number 5 is at 18. We're going to say the cover here is going to be 0.75, and then this will be half of the bar diameter plus the 0.75 for the CG for number 2. Actually, it'll be a full bar diameter, so this will be 1 point, let's say 1.38. Okay, and that's bottom still. Now, if I wanted to turn on the tag for that bottom reinforcement, we could go to visibility, view settings, and for mesh rebar, I could turn on, let's say, the dimension, and that will show me the bars in that location. Okay, now we're going to add an additional 4 number 5 bars in the outer bays. So let's go ahead and do that. We'll go back to rebar. I'm going to select distributed rebar. The first thing I'm going to do is just select the length of the bar. So I'm going to just position a bar. We're going to say that this bar is 15 feet. And the bar distribution, it says make the first end of the range. So we're actually going to assume that the bar goes from the extents of this bar. Let's say go from here over to let's say here, and that gives me some range. Now that range is arbitrary unless I have something to actually snap to reference for an actual dimension. So now that I have it entered, I can go in and adjust some things. So we're going to say that the spacing of those bars over this range can be fixed, or you can have a fixed number of bars. So we're going to turn off, we're going to go ahead and say the spacing is going to be 12 inches on center, and I want to fix the number of bars. I want the program to calculate the number of bars, and if I update that, you can see the program will say, oh, you have 8 number 5s, or you can specify the proper number of bars, and the spacing doesn't technically matter in this case. So we have 4 number 5 bars. Let's go back and make sure we fix that. We said there would be an additional 4 number 5 bars in that zone. I can change the extents on either side, so it can either be grouped or distributed. Technically, it doesn't really matter unless you're trying to get a perfectly accurate layout of the rebar, because the design cut that extends through this particular bar is going to consider it whether it's grouped or distributed anyway, and it always considers it as a lump sum, a lump area of bar at the centroid, of the section with respect to the effective depth of the bar group. So this might be just for presentation purposes, but we'll go ahead and I'll just move this range, from there to the edge of slab, and then this this range I could actually extend down if needed. So anyway, that's how you could put in a range of that bar for distribution. But again, it's not something that's super critical if you do that versus, let's say, grouped reinforcement. Okay, we're now going to go ahead and extend the range here, and I'm actually going to say that this is a 15-foot bar, and we're going to use 8 bars here in this bay. Okay, we're going to have no additional bar in this midspan here, and then we'll go ahead and copy this down again. We'll just reuse that. Make sure we snap to the right spot there. So there's 1, and I'll reuse that there also, 2. And I'll just leave those as is. You've seen how we can edit those and manipulate them. In the other direction, I'm going to actually model these as banded. So we're going to do a bar here that's 15 feet. We'll say that's 4 number 5s, and then I'm just going to take that and copy it over here. I'll copy it there, and we'll copy it over there. Okay, so this is the base reinforcement in this slab in this particular bay that we are evaluating. And I'll go ahead and turn on this, or turn off the rebar by selecting show rebar. That turns it off and on. I'll do the same for loading. I'm going to turn off the loads that we have, and now we're going to add some post tensioning. Now the post tensioning, we're going to assume, we're going to say we have 10 half-inch diameter strands here as banded, and then here we're going to say we have 16 strands as banded, and then we're going to run distributed cables down, and I'm basically just going to run them along this frame line. So we're going to have a reverse parabola here, a reverse parabola here, and then we're going to use just a cantilever down shape and anchor them along behind this line here, this frame line. So that's how we will model the tendons. Again, we're only going to set up strips in this region anyway, so because that's our area of focus for this particular evaluation. So let's do the banded first. I'll go up to Tendon, Add Tendon, and I'm just going to select the edge of the slab, and I'm going to use snap orthogonal, and I'll snap to this column, and then I'm going to turn off snap orthogonal and snap perpendicular, and I will press enter to close that. Okay, so that's one tendon line. We'll say that this actually represents 10 strands. These are half-inch diameter, 0.153 for the area. The stressing of the strand we can either assume as an effective force or assume calculated force. So if you know the tendon anchorages, if you know the jacking stress, and if you know the lump sum long-term loss, you could go to calculated force and actually enter that, and the program would calculate those losses for you. That may be more accurate, I think, than effective force if you can actually replicate the same force profile for the tendon using this input. In our example, we'll just assume that the average effective force for that cable over time, we'll say, is going to be 26 kips, and we'll just enter 26 there. The left side is going to be the dead end, the right side will be the live end. Graphically, that's the only impact that this has when you're using effective force. The actual dead live, live dead, or live live impacts how the program calculates the force if you use the first option. For shape, this allows us to define the shape of the tendon. So we're going to assume that the anchorages are at 4 inches. We'll say that the end spans are 1. We're going to actually raise the interior span, let's say, to 2. And this might be just taken off the drawings that you have for the PT. So this is our profile for the harped, for the banded tendon. And then I'm going to take that and just Control C, Control V, and we're going to copy that down. Let's see. Actually, let's not copy this. This is too much of a difference. We have 2 extra spans here, so we'll just go ahead and draw another tendon here. So we're going to draw one tendon that anchors here, and again I'll use snap orthogonal. I like to use that tool just because it's a little easier to move away the cursor and then just see where the tendon's being drawn versus being right on top of it. And then we'll do a cable point there, and then I'll end it again using perpendicular. We want to turn off snap to nearest, and we'll add another tendon. I use snap to nearest to actually start the tendon line or the tendon point, and then I turn it off because it becomes a little more cumbersome to use beyond start points. Okay, and then we'll run a span across the wall. That will be just a straight span. I'll turn off also snap orthogonal once we get to the end span. So here I'm actually modeling 2 tendons that represent the total of 16. So we'll do 8 and 8. The reason I'm doing that, I like to just balance the force on either side of the frame line, and I have a dissimilar tendon. This tendon actually on the top cuts short because of this corner here and this tendon running out towards the wall. So we're going to use again the force of 26 kips. The shape here will be reverse parabola. We're going to change this again to 2 inches here. This will be 1 inch, and then on the opposite end we're going to have a straight shape like so, and we're going to run that out to the edge of the slab. We're just copying what would be on the plans, and we'll assume that this is the shape of that cable. or those cables. This will be 8 also. And on this end, we're going to create a straight span on span 1. Again, we'll raise that to 1. This will be 2. The last span is also straight. And we'll say this is 1. Okay, and then the stressing again is effective 26 kips. Make sure that this is also set to 8, which it is. And those are the banded tendons. Now the distributed tendons, again reading from plan, we're going to assume that we have 2 tendons every 3 feet. And so we have a change in the slab edge here, so we're going to have to be mindful of that. So we're going to model these tendons here first and then these tendons second. I'll go ahead and add a tendon, and this tendon, let's see, actually we're going to model, before we do that, let's model one more. This is almost a dummy tendon, but in this case we need it to reference the distributed because we said we were going to anchor the distributed behind it. So let's add one more set of banded tendons here, and these will also be 8 strands. So I'm going to go back and actually we're just going to copy this one. We're going to say Control C, Control V. I'm going to say 1 and 2. And all we need to do here really, they're already set to 8. We're just going to change this back to reverse parabola. This is a shorter span, and we're going to raise that profile, let's say up to 3.5. Actually, this should be 4. Let's drop that down to 2.5. Here we're going to change that to reverse. Again, 2.5, and this will be 4. One thing I failed to mention, these are unbonded tendons, so you can either change the system to bonded, unbonded. If you are using the calculated option, then mu and wobble for the friction losses will come into play, so you'll want to enter those as well. Okay, so we have that one. I'm actually going to delete that one out, and we'll go back and just copy this one, and then we're ready to go. So the distributed cable will start at the top, and actually let's start at the bottom and work up. I think that'll be easier for us to see in elevation, and we won't have to work backwards. So we're going to just start out here. This will be the first span. So again, I'm going to use the orthogonal tool. This is 0.1, 0.2, and then I'll use the edge of slab as the last point. Turning off orthogonal again. We're going to set this to 2 strands. Stressing will be 26 kips per tendon. This first span will be a cantilever down shape. We just have to terminate it somehow. It might actually be a cantilever up shape given the actual profile of the cable. We might even drop that down. We're going to leave it at 4 here for this example. But in reality, you may actually model the full extent of all of the tendons in this in your investigative model. So the profile will be 1, and then we're going to just use 1 here in these middle bays as well. And then the end span will also be 4 shown there. And what we'll do is we'll take that and we're going to just space it at 2 feet increments. So we'll go to Modify, Copy by Coordinates. It will be in the positive X direction every 2 feet, and we're going to copy this. I'll just say let's say 10 times. Say copy. Okay, that didn't quite get us there, so we'll do that again. We'll say by coordinates, and I could have measured that first. I just am essentially guessing what that really needs to be. We'll say 6 times copy. Now here we're going to go ahead and just delete this. Actually, let's go back and keep it for just a moment and manipulate it because we still want to keep that 2-foot spacing here. So what we'll do is take this point and just move it out like so. And I need to add an additional span. So I'm going to select this. I'll right click, say Insert Vertex. And that inserts a high point right here. And I'll take that point. You can see there's a square handle on that point. And I'm just going to move it to the intersection. So I'll use Snap to Intersection and move it to that point. And now if I double click on the tendon, go to the shape, you can see we have this tiny little span that's actually a cantilever, and I'll use a cantilever down shape there. And I'm actually going to drop the CG like so. We'll make it exit straight on that location. So now we have our second shape for the distributed, and I'm actually going to copy that over 30 times. So we'll go by coordinates, 2 feet. I think we said 3 feet at first, but we'll use 2 feet. This is probably over post-tension in terms of pre-compression, but we have something here. So we'll go ahead and copy. I'll copy that a couple more times. Okay, so I think again, I think we have too much PT here, so I'm actually going to delete out. We're going to say we have 2 tendons every 4 feet, and I'm actually going to delete some of these tendons. So we'll delete every other cable, and I'm just selecting and deleting those out. I could also just control. That might be a bit faster. Okay, I'll leave those 2 on the end there. We'll get rid of it. Okay, so we have our distributed now. And we have our rebar. If I go back to rebar, show reinforcement, we have our rebar in that end span. So now we want to evaluate the slab. To evaluate the slab for stress and for capacity, we have to generate design strips. So we're going to create what's called a support line in the X direction along this path, along this frame line, and along this frame line. And by doing that, the program will be able to break this up into a tributary. Here's the tributary for the top frame line. But the bottom frame line, the program doesn't know where to end this tributary unless we impose a boundary. Now, if we're only doing a partial or a portion of the slab, we have to use what's called this splitter tool. And that splitter tool will be put here so that the program knows to end the tributary there. So this is pretty easy to do. We're going to go back to the default display. I'll turn off the tendons and the rebar. I'll go to floor design, and I'm going to create an X direction design strip. And I'll start this strip out here at the edge of the slab, and then I'm just going to snap to each of the columns. Okay, and again, I'm using the snap tools to my advantage. I'm turning those off that I don't need and using those that I do need. I'll turn those on. Here I'll snap to the edge of the wall, the opposite edge, and we're done with that. Now I'll go ahead and add the splitter. I'll go to create X direction splitter, and I'm just going to assume that that splitter needs to be put here, and I'll use snap orthogonal to create a nice straight line. Now if I generate the design strips at this point, if I go to generate sections new, this auto generates the tributary regions and the design sections relative to the modeled support lines and with the associated properties. So this support line, if I double click, is set to design as a two-way slab. That sets the design criteria or the investigative criteria. We're going to generate 12 sections per span, so that basically 12 design cuts per span for this, and that's the same as this strip here. So we'll go ahead and generate. The program generates 2 tributaries. There's tributary 1, and I'll select under strip results visibility, I'll turn on the outlines. And you can see I have 2 strips that I'm evaluating in the X direction. I also want to evaluate the Y direction. So these look nice and clean. We'll leave these as they are. We'll go to delete the design strips. That basically removes them, and I'm now going to generate the Y direction support lines and splitters. They have completely no relation to the X direction support lines and splitters. They're completely independent. So I'm going to turn off those 2 options, support line, and I'll turn off the splitter, because we don't want that to confuse what we're doing with the Y direction. I'll go over here now to Y direction, and I'll say, okay, create the Y direction strips. And for this direction, I'm just going to start again somewhere below this frame line. All I'm worrying about really is this area here. So I'll actually start back here, and I'll click a point as my start point. I'll turn off snap orthogonal because that becomes cumbersome in this case. I'll snap to the endpoints of walls to the column, and then I'll stop this at the slab edge, press enter, and begin drawing my next one. So there's point 1, 2. I'll press backspace if you miss snap. There's point 3, 4, and in this case I'm going to extend this out of the slab, and I'll tell you why here in a moment. So that's point 5, and I'll come back point 1, 2, 3, 4, and then perpendicular is 5. Here I'll go 1, 2, 3, 4, 5, and 6. Okay, now in this case we have horizontally the program can determine where to put the divisible lines, let's say, for breaking up the tributary. So here's tributary 1, here's 2, here's 3, and then 4. But it doesn't know how far below to extend the tributary because the boundary that it sees below this point is really the slab, but the support lines kind of stop arbitrarily just inside of the slab. So to make sure we have a nice clean break for where the tributary regions are generated, we're going to create a splitter chaining these points together. And this splitter will be called a Y direction splitter. Again, it's just a boundary that we're imposing. And we'll go and snap nearest. I'll turn that off. And now I'll just snap on each one of these endpoints that I've created. Turn back on, snap perpendicular, and close that off. And we're done. Now, if I generate the sections again, the program will generate sections for X and Y directions. And I can control those visibility of the visibility of both over here. So we'll turn off both using this option, or turn on both. If I turn on the Y, there's 1, 2, 3, and 4. And if I turn on the X, 1 and 2, and this turns it off and on. If I look at the Y direction tributaries, those are the Y direction tributaries. Okay, so now I have the tools necessary to evaluate the slab. Now the first thing we want to do is evaluate the demand and capacity. So we're going to mesh the slab first, and we're going to then analyze the slab for whatever set of combinations we want to evaluate for the run. So I'll go to Analysis, Mesh. I'm going to use a simplified meshing. I'll use a uniform mesh with the default sizes here. We'll say Save and Mesh the slabs. Once we've done that, and notice it looks a little bit messy here because I have the design cuts turned on. I'll turn those off. And I'll even turn that splitter off, the Y direction splitter. Turn that off. And now if I go to Loading Combinations, we have a few default combinations here. Well, these are based on the code that is selected in the criteria. So we haven't really explored any of this. This just allows us to set the design code, which may or may not be of benefit given the investigative nature of the run. We can set the design code, which preloads a few gravity-only combinations. We also could set the allowable stresses. So we're going to use that when we evaluate the stress. And then the other stuff for tendon heights and rebar cover and that's more associated with the actual new design. Okay, so let's go ahead back to loading combinations. In this case, we're going to do a couple of things. We're going to get rid of initial because that's really for new design when the tendons are stressed. We don't necessarily need to check that because the tendons are already in place. We're going to evaluate the slab for strength dead and live and strength dead load only. Well, we added this future tendon load, so I'm actually going to add a load combination there of, let's say, 1.2 to this new load. And we're going to check moment, demand, and capacity for strength, and then we'll check the stress at total service load with the new loading. We'll call this 1, and then for the sustain we're going to say, well, let's evaluate it also with 50% of that new loading. And you can add new load combinations as you need to for your own investigation. So we'll go back to analysis, and we're going to select execute analysis, and I'll run this for those 4 combinations. The uncracked means that we're just using a stiffness modifier of 1. Nothing is assumed cracked. The program does allow you to modify the components by adding what we call new usage cases, where you can assign different modifiers. We're not exploring that here in this example. And then these settings we're going to just leave as they are. We'll go ahead and select OK and analyze the model. That's done analyzing. The next step will be to go to floor design, and there's 2 options. We can design the sections that we've created, and I'll go to my default display and turn on the sections in the X direction. So we have X and Y sections. We can either design these, meaning if the program needs to add more reinforcement to meet minimum requirements or strength, it will add rebar above and beyond what we have in the slab currently. Or we can investigate. So in order to check demand capacity based on the existing reinforcement and the existing post-tensioning, we're going to use investigate. So I'll select investigate. And that's done. And now we can graphically or in tabular format check demand capacity. The first thing is this result display settings dialog will open. In this dialog, I'm going to navigate down to design sections. In design sections, we can see we have actions listed: bending, and if you turn on the bending actions, the program will by default show max min on each strip. If you turn on the numerical display under strip results / visibility, this will show you the demand moment for the selected combination in the result display settings. So if I go to envelope of strength, these are the strength demand moments we want to evaluate whether we have enough capacity for. This is the envelope of those strength moments. We could also look at axial force, shear, and so on along those design strips. We could also look at deformation. So for deformation, if I go back to service total, for example, the program will report the elastic, immediate elastic deflection that's integrated over each design cut line. So for example, the max here is 0.7. If we take this span length between 0.1 and 0.2 on that support line, divided by 0.7, we get L over 600. So that's a quick check we make for those deflections in the slab along the strips. And you could do that actually for both directions here. This back here may not even pertain to anything because it's just a half span. It doesn't really mean anything in terms of what's happening in this bay here. But that allows you to look at a quick deflection check. Ultimately, we want to go down here to investigation, moment capacity, and you can see there's a couple of things shown. There's the green is the negative or the positive capacity of the section. The blue is the negative capacity, and the program will report the value again on every design cut. So for example, here at the midspan, the capacity is 261.5, that's positive, negative 23 for negative. The next number, 0.76, is the demand capacity ratio. So this is based on the enveloped strength moment divided by the capacity. And you can see that's meets 1, it's less than 1, therefore the design cut is green. The demand capacity ratio on the negative moment side is 0 because there is no negative moment as an enveloped value at that design cut. Once you get over a negative moment region, now we have this kind of flip. We have negative 187. The demand capacity here is actually 2.16, which is greater than 1. We have a problem there. And then this is 0 because, again, there's no positive bending as part of that envelope at the support location. and the program will report where you have a demand capacity ratio greater than 1. Those are flagged in pink. So here at this midspan, it's 1.1, 1.19, 1.09, and up in the top left it will show what the maximum demand capacity ratio is for any location X or Y in the slab for your design cuts. And it may be in the other direction. If I toggle this, you can see this is 1.16 here, 1.28, and so on. Now, notice also that if you have a design cut, for example, we have actual design cuts back here, the program will check those design cuts also. So we may want to avoid what's happening back here, but if we put a support line back there, we're going to get results. So in our case, we're really only concerned about what's happening up here, so we just essentially ignore that, or we don't extend the support line back there, and we would actually put a splitter here, and all of this would basically go away if we're doing a partial evaluation or a evaluation of a partial slab in this sense. The next thing to note is the moment capacity with demand. So I'll go back to the X, it's a little easier to see. If I turn that on, the program will show me the demand moments. So you can see there's this gray region. The gray region is the demand. And when it turns pink, where you have like these pink peaks, that means that the demand exceeds the capacity. So that's just graphically showing the locations where you actually have overstressed areas. From a tabular standpoint, the user can go to reports, and you could select the option here under design strips, and if you select the forces report and also the moment capacities report, you could compare those also in a tabular format and report the same data on the design sections as what we're seeing graphically. Okay, if you wanted to see how much rebar is needed to meet the demand moments, we would go back to floor design, and we would actually design the sections versus investigate. Now, in order for us to check stresses in the slab, the program is actually currently hard-coded to check stresses only when we design. So we have to run this again using the design option to check stress. We're not going to really focus on the demand capacity, because by doing this, the program also adds rebar to meet capacity. And if I select yes, and I look at these diagrams, you can see a lot of that pink went away. In fact, the only pink options that are shown are areas where the designer didn't converge exactly below 1.001, let's say. So these still flag as pink because the convergence has a little bit of noise in it, if you will. So that's actually being resolved for Builder 18.1, but that can happen in Builder 17 or Builder 2018.0. But for the most part, these are within 1 or a very small percentage greater than 1 due to that convergence. But again, our objective by designing is not necessarily to see what the demand capacity is, but to see what the stresses are. So if I go up here to stress, bottom stress, we can see that our allowable is 6 square root of F prime C, which is 424 for this slab, and we're well over that in many of these spots. So this shows us the actual stress in PSI, and it shows you how far over you are from the 424. And we would toggle again to the other direction, and we could also look at top stress. So in the top, if I toggle back under floor design to X, we have some pretty severe stress issues here at these columns. That covers the essentials for investigating a slab inside of Builder 2018. If you have any questions or concerns, please contact us at support@adaptsoft.com. Thank you.